Yeah. Okay. So good morning, everyone. My name is Xin Wang. I'm from China Agricultural University. I'm the chairman in this session. So I'm working on Wageningen University of and research for tomato robot project. And the first presentation will from Ilgen. The topic of this presentation is optimal tuning of the SMC parameters for two-link manipulator co-simulation control. So, Ilgen, now I will give you the floor and please take your time.
Okay, thank you.
Okay.
Good morning, everyone. My name is Sinan Ilgen. I'm attending electronic conference from Turkey, and I am a research assistant at Karatay University in Koniar, in Department of Mechatronics Engineering. I will talk about today our paper, which is entitled by optimal tuning of the sliding mode controller parameters for a two-link manipulator for simulation control. In this paper, we try to present the trajectory tracking control of two-link planar robot manipulator using Adams and MATLAB softwares with co-simulation operation. These are the contents of the presentation. Firstly, a brief introduction I will give, and then the details of the study will be explained step by step. And lastly, I have a conclusion and perspective parts. Let's start with the introduction part. As you know, as everybody knows, the robot manipulators have widely using for a wide variety of basic industrial operations, such as material handling, machine loading, or welding, etc. There is lots of examples. In general, the robot manipulators usually consist of rigid links, have connected each other by the joints. These joints that allow the motion of the neighboring these rigid links. The robot manipulator have easy installation, easy usage, and they have high mobility in the industrial areas. In general, when we check the literature, 2 or 3 degrees of freedoms manipulator system is commonly used for different applications. Also, there is some studies on the which 4 or more degrees of freedom have also been reported in the literature. First step of our study is system modeling, because system modeling is a very important part of these robotic systems. In our study, for virtual prototype of the manipulator, we use Adams software. The first step is modeling in Adams, and then after we Adams process, the designed manipulator is exported to the MATLAB Simulink environment for carrying out the controller implementation. And then finally, co-simulation stage is performed to simulate the movements of the manipulator. And these are the screenshots of the manipulator from Adams environment. 3D dimension, 3D view of the robot manipulator is like that. These are taken from Adams software. When we look to our manipulator model, the two-link manipulator is able to move only X and Y direction. We can think like a coordinate system. Our system, as you see in the picture, there is 2 inputs. These are T1 and T2. They are torques of the actuators. And we have to control 2 outputs. These are joint angles, θ1 and θ2, as you see on the picture. There is some system parameters it's on for robot manipulator. These system parameters are defined in Adams. You can see on the table, for example, mass of the links or length of the links. And the unit of the torque or angle of the joints. These all parameters are defined in Adams environment. I want to give a short summary of the co-simulation methods. In co-simulation methods, as you see in the picture, the Adams software and MATLAB MATLAB software is working simultaneously. When in this operation, the output of the Adams model, output of the robot manipulator is at the same time is controller inputs for the MATLAB system. Yeah, we think Adams is represents the system and MATLAB represents the controller unit. Likewise, controller output of the system is input of the Adams model. This is the basic methodology for MATLAB Adams co-simulation methodology. When we export these 3D robot model into the MATLAB Simulink environment, you can see in the right side picture there is a orange box. Is the manipulator comes to the Simulink environment like a box, as you see the orange box in the right side picture, and the other side of the picture is completely controller design of the system. We can look to methods and technologies parts. Firstly, in MATLAB Simulink sites, we try to create this block diagram for the system control. As you know, there is a, for robots movements, there is a transformation between position and angles of the joints. These equations named as kinematics. Here we have to use inverse kinematics because the manipulator should go to the our desired position. To perform this task, we have to attain the suitable joint angles in on the picture θ1 D and θ2 D. The equations of the inverse kinematics are manually calculated, and then these equations are embedded in MATLAB Simulink like that. After we get the joints angles, suitable joints angles, the controller procedure will start. As you see on the block diagram, we used two different type of controllers. One of them is sliding mode controller like SMC, and as you know, the other controller type is most generally mouse controller, PID controller structure. Again, same picture. These are the controller hierarchy on the MATLAB Simulink environment. I want to give a brief summary about the sliding mode controller. Sliding mode controller is a special type of variable structure control systems. It's generally used for the nonlinear systems. And Russian sciencemen Emelianov and Utkin is the first working with the sliding mode control, is the father of the sliding mode control, we can say that. And these controller type sliding mode controller has some advantages like insensitive against what are these? For example, parametric change of the system. If there is a parametric change of the system, the controller mechanism can be behavior insensitive. The other insensitive is external disturbing effects or errors in the modeling. The sliding mode control is completely insensitive against these disturbances. Expectation, what we want to do in this study, we have two scenarios for our robot manipulator. First one is 2-position control, and the second one is 5-position control. For the 2-position control, we try to implement of PID and sliding mode controller structures at the similar conditions. And scenario 2, just be focused on the sliding mode control with we try to optimize the coefficients for the controller to get better performance for the robot manipulator. At first, two-position control, we think like that. We put the robot manipulator on the origin in the XY coordinates system, and the end effector position of the robot manipulator is in X direction 0, and in Y direction 350 points. We want from the robot is it should go the first point and second point. We have two positions. First point is 250 point in X and Y direction, and second point is 50 in X and 200 in Y direction. These are the first scenario. We used PID and SMC controller structures. It is performed on the MATLAB Simulink environment, and we have to we defined the required parameters for also PID and SMC is occurred by using response optimization toolbox on the MATLAB Simulink environment. For scenario 2, again, the initial position is same, but in this scenario, we wanted to make a bit difficult for the robot movements. We defined 5 different positions, as you see in the table. For this one, just we used sliding mode controllers. Also, we performed these control structures on MATLAB Simulink, and also we defined the all coefficients, all parameters for sliding mode controllers under response optimization toolbox. In difference from scenario 1, in response optimization toolbox, we compared 3 different optimization algorithms: gradient descent, pattern search, and simplex search. These all optimization algorithms is ready for use on the Simulink environment. When we check the results for the first scenario, two-position control, as you can see, the robot manipulator is put on the origin of X and Y coordinate system. At the same condition, the blue one is sliding mode control, as you see, and the red line is represents PID controller. When we compare these results, the sliding mode controller is more efficient than the PID controller performance at the same time. We can check the coordinates result. This picture represents the X coordinates system. Firstly, I want to share this information. We planned the total movement of the robot is 10 seconds, and in first 5 seconds, the robot should go to first location, and then between 5 and 10 seconds, the robot should go to second position. If we check this graphic, for green line for reference, the sliding mode controller has better performance than a PID control structure. And for the Y coordinates is shown in this figure. Also, there is a good performance with respect to SMC sliding mode controller compared with the PID. And these two images for the fast portraits of sliding mode control. These two graphs is important for the sliding mode controller structure. How can we understand this? How can we explain this graphic? For first 5 seconds, for movement 1 location for location 1, the blue line is the important thing is the error is converged to 0 at the beginning of the movement. It is 0, but while the coordinates of robots is changing, the error will become, I can show like that. At the first, it is 0, but at the with some time, the error is not zero, but at the end of the position, the error and derivative of error is nearly zero. Also, for the second location, at the end of the movement, the error and the derivative of error is converged to zero. These images for theta 1. For theta 2, also there is two-part location 1 and location 2. Both of the movement sides, the error and the derivative of error is converged to zero, as you can see. Let's check the 5 position control results. Again, we put the robot manipulator on the origin in the XY coordination. As I said, there is totally 5 locations. There is totally 4 graphs because, as I said, I have used 3 different optimization algorithms, and an extra, there is no optimization here, just trial and error methods. We want to compare 4 of them. And when we check the graph, the pattern search is orange line is very bad performance at the same condition for these optimization algorithm. And then we check the others optimization, gradient descent or search simplex, and trial and error methods coefficient is better performance than the pattern search optimization algorithm. If we can check the, again, position, 5 position control for X coordinate, as you can see, the one of them, just pattern search, is a bad result at the same condition, but the other optimization method or non-optimization results have a good performance for 5 different position control. Also, the same results for the Y coordinates. The pattern search result is better than compared with the X coordinates. These are the results for the 5 position control. Conclusion, why we did this study. When we see in the literature, there is a lack of knowledge in Adams and MATLAB co-simulation operation. There is a few studies. There is lots of studies for different softwares, for example, SolidWorks and MATLAB, or ANSYS and MATLAB. There is lots of work, or CATIA and MATLAB. Again, there is lots of study, but there is a lack of knowledge in Adams and MATLAB co-simulation. We think that there is these co-simulation operations presents an efficient solution in simulating and controlling of the nonlinear systems, such as robot manipulators or other nonlinear dynamic systems. We think that it can be, these studies can be based for the future works about simulation and control of the robot manipulator. What is our future projections? This study is not finished, of course. We have to improve the controller performance, for example, decreasing settling time, or we have to acquire no overshoot results. And we will try to make these control operations with under payload. In this study, there is no payload for our scenarios. And move to we want to try to robots to move different positions with some different payloads. And thank you for your attention. If you have any questions or comments, I can do. Thank you very much.
Okay, so thank you very much, Ilgen, and thank you very much for your nice presentation. So now it's okay. So now it's question time. So is there any questions? You can open your microphone, or also you can put your questions in the chat. Okay, so I have questions first, maybe. So in slide 12, I see a picture from your presentation, and you said this effect from SMC model controller will be more efficient than PID. So can you explain it?
We define the controller parameters on the response optimization toolbox at the totally same conditions. This is a reduce software. We just run the program and get some coefficients for PID or SMC. We didn't do any changing of these parameters. We can apply to the system. The results of the system is like that.
Okay, but you said it's more efficient. It means that you need not change any parameters from your model. Yes. Okay.
Yes.
Yeah. Okay. So if it's not any other questions, I will thank you, Ilgen, and I will give the floor to Kristian Takacs. Kristian Takacs, are you here?
Good morning. Yes, I'm here.
Yeah.
Can you hear me?
Yeah. Yes. Can you share your screen?
Yes. A moment, please.
Yeah. Okay. Yeah. Okay. So now I will give the floor to Kristian Takacs. The topic of his presentation is control of robotic arm with visual system. So please take your time. Good luck.
So good morning, ladies and gentlemen. I would like to quickly introduce myself. My name is Kristian Takacs, and I am a first-year PhD student at the University of Žilina in Faculty of Electrical Engineering and Informational Technology at the Department of Mechatronics and Electronics. Now I would like to share with you our paper on topic control of robotic arm with a visual system. This paper was created in collaboration with my colleagues. In this presentation, I will talk about the design of a sorting system that is able to sort objects based on their color, shape, or its combinations. Next, I will talk about the analysis of the used hardware, searching methods and sub-algorithms, implementation to the lab environment, and testing the reliability of searching methods. The hardware design of the proposed sorting system consists of a camera with a lighting source, and robotic arm, and a superior computer. The left side of the screen shows the used camera sensor. The SIMIA camera is designed for a machine vision application in industry. Its resolution is 1.3 megapixels with a frames per second rate up to 200 FPS. This camera is used for capturing an image of the workplace located in front of the robotic arm, and the camera is attached on a static tripod with a macro zoom objective. The right side of the screen shows the used robotic arm. The robotic arm from Dubot is a multifunctional 4-axis manipulator with the possibility of connection variables and devices. The robotic arm is intended mainly for teaching purposes. With this arm, the found object is transferred to a predetermined location with a vacuum suction cup or a pneumatic gripper. The configuration of the robotic arm was based on the analysis of its kinematic equations, operating modes, and communication with the superior computer. From this analysis, the location and the size of the workplace was determined, which the size of this workplace is 20 by 10 centimeters. The left side of the screen shows the area in which the robotic arm can move, and the right side of the screen shows the robotic arm in the Cartesian coordinate system. After the hardware analysis, process software for the sorting system was designed in the Labio environment with a GUI. The graphical user interface of the sorting system is shown in the left side of the screen. The right side of the screen shows the block diagram of the process software. After the user selected the shape and the color of the required object, selected a type of the searching method, and enabling or disabling the image balancing sub-algorithm, and pressing the start button, the main software software of sorting algorithm begins. The workflow of the algorithm is as follows. The camera captures a scene of the workplace on which are the objects randomly situated. Then the captured image is proceed with the image balancing sub-algorithm. Then the selected searching algorithm or method starts the searching the selected color or the selected shape of the object. If the algorithm doesn't find any matches, then an error message occurs on the GUI. If the algorithm does find a match, then calculates the center of mass of the each matching object in the image. This value is in pixels, so the algorithm transforms the values to the corresponding form for the robotic arm, which picks up the found objects and put them aside. As a last step, the endpoint of the robotic arm moves back to its home position, which does not interfere with the view of the robotic arm. Next, I would like to show you the concept of some used sub-algorithms. The left side of the screen shows the block diagram of the surface height mapping sub-algorithm. The height mapping of the workplace uses an effector with a mechanical button, and it is needed to assess if the work area is absolutely flat or to compute a lookup table of the height coordinates for each point of the workplace surface. In the selected measuring key points, the workplace, the robotic arm decreases its height coordinates until the button touches the surface of the work area and changes its logical state. This state is evaluated through GPIO pins of the robotic arm. The actual height coordinates are saved to a calibration file, and refinement of this height map is reached using a bilinear interpolation of measuring key points. The right side of the screen shows a block diagram of the position controlling sub-algorithm. Later in the process of attaching the object to the suction cup, we must consider the Z dimension of the object. Then the sub-algorithm processes data from object detection algorithms. One of the main output value of these algorithms is the center of mass of the desired objects. The sub-algorithms initialize the suction cup compressor before transferring the object. Then the conversion of obtained data from object detection algorithm into the processable data type for the robotic arm is executed. Logical signal driving the compressor of the suction cup is coupled with the motion of the robotic arm. After the object is attached with the suction cup, the arm moves to a predetermined location where the suction cup is turned off and the object is released. Since some algorithms use segmentation based on color information, we must correct the input images to provide a white color balancing. So the shift of the color spectrum is in the captured image occurs because of the CMOS sensor of the use camera and use LEDs in the light unit emits a light in the blue part of the color spectrum. So correction of RG and B gains in the camera sensor must be set up in the hardware way, or the accurate image must be balanced by the software way. In the simple way, the principle of the operation of color balancing subalgorithm is to calculate the correction heights for the individual pixels of the R, G, and B layer based on a selected pixel in the image. Applying the white balance serves also a normalization of input images in an aspect of a color sense. The left side of the screen shows a block diagram of the searching method based on shape factor subalgorithm. The subalgorithm first converts the image from the RGB space to the HSI and extract the intensity layer, which contains the information about the presence of objects in the image. Then the normalized compactness is calculated from each object in the modified image. Based on the value of normalized compactness, the subalgorithm is able to define the selected object. The shape factor computes the compactness of each object segmented from the image based on equation 1. But to normalize these values to interval from 0 to 1, we often use a formula for normalized compactness based on the equation number 2. The right side of the screen shows a block diagram of the pattern matching subalgorithm. This method search also requires that the image must be converted from RGB space to HSI before the process of searching for object begins. And unlike the shape factor method, this method requires a template that contains the shape of the object. The principle of operation of this method is based on moving the template across the image according to normalized cross correlation technique, while at each point the algorithm calculates the correlational score. Because the underlying mechanism for correlation is based on a series of multiplication operations, the correlation process is time-consuming. The left side of the screen shows a block diagram for the geometrical matching subalgorithm. This geometrical matching search method, like the previous method, required a template for detecting object and converting the original image. The principle of operation of this method is that the algorithm extracts the information of the curves from the template and then compares the curves and their coordinates in the grayscale image according to the gained information of the template. The algorithm recognizes objects based on their geometric shape, and the algorithm calculates the correlation score of each object. The right side of the screen shows the block diagram of the color-based object searching method subalgorithm. This method allows the user to select an object of a specific color from a scene. The subalgorithm first converts the image from RGB space to HSI and extracts the hue layer, which contains the information about the presence of certain colors or wavelength range in the image. If the position of each color in the hue layer is known, then the subalgorithm can execute the global thresholding of this layer to detect the object of a specific color. After a basic morphological operation, the subalgorithm computes the center of mass of each object. The proposed sorting system in form of the laboratory setup for testing the reliability of used searching methods is shown in the left side of the screen. The testing was focused on measuring the reliability and speed of previously mentioned searching methods for searching a specific objects in the captured image of the workplace. The right side of the screen shows the comparison of captured original image of the workplace and the balanced version with the phantom objects in form of simple geometrical shapes. In the center of the screen is shown a comparison of the testing, the reliability of each searching method. The left side shows a bar chart of correctly detected objects of each used method. And the right side of the screen shows the bar chart of searching time and average searching time of each use method. The result of that measurement is that by using the color balance sub-algorithm on the original image, we can increase the percentage of correctly detected object, minimize the number of falsely detected objects, and speed up the average object search time by highlighting the edges of the searching objects. So in this presentation, the design and analysis of a certain system was described. So it is possible to sort objects on the captured workplace by color, shape, or their combinations. In the GUI, the user is able to choose which of the mentioned method is used in the object searching process. The software of the sorting system was designed in the lab environment, and also the color-based searching methods, the searching method based on shape factor, the color balancing sub-algorithm, and a sub-algorithm for controlling the robotic arm were implemented in this environment. Thank you for your attention, and feel free to ask anything.
Yeah. Okay, thanks, Kristian. And so now it's question time. Is there any questions for him? And please open your microphone or put your questions in chat.
May I ask a question?
Yeah, please.
Yes, I'm from Turkey. I'd like to give regards from Turkey. My question is, you use a simple robot. Is it possible to use very complex robot for this image processing algorithm?
It is possible, and the method of using a more complex robot is based on the communication between the used arm and the superior computer. So it must know the communication packets of for the driving the robotic arm.
You mean the system is universal? You can use for every robot?
Yes, by changing some of the, as I said, of the communication packets.
Okay, thank you very much. It is
You're
very
welcome.
good work. Congratulations.
Thank you so much.
Okay, is there any more questions? Yes, maybe I also have questions for your visual system. So you said your system is use some algorithm, color-based balance algorithm. So now it's only used in blue color light, or also you can extend it to different color light. And how you consider the illumination issue? Yes, please.
So the first part of your question, this color balancing algorithm is universal. It works on the principle of that the algorithm choose a white pixel, and from this pixel the height of each pixel from R, G, and B layer is like updated. So it is possible to change the red or blue or the green color.
Yeah. Okay.
And
So yeah, please.
and you ask for the illumination.
Yeah.
I sorry, but I don't understand this part of your question. What did you mean?
Just like now, you do the experiment in the indoor environment.
Yes.
So have you considered about if you put your object into outside, what will be the issue for this?
We don't experiment with this environment where the light could change, but it is possible that each searching method could find more phasally through two matches of the objects, or could not find the required objects.
Okay. Yeah. Okay. Thanks a lot. Thank you very much. Thank you for your nice presentation, Kristian. Yeah.
My pleasure.
Okay. Okay. So now I would like to change to the next presentation. So Andruskiene, are you here? Maybe you are mute. Jurgita Andruskiene.
Yes, yes,
Yeah.
here. But
Yeah.
the presentation will be by Professor Sertac.
Oh, Sertac. Okay, Professor Sertac. Okay. So good morning. Can you share your screen and?
As I know, the program changed, and we are going to present our study. Am I right?
Yeah. Yes.
Okay.
Yeah. Okay. I will try to do a brief introduction, and you can start later. Yeah.
Okay.
Okay. So this topic for this presentation is controller gain tuning of a non-holonomic mobile robot while neural network predictor. So the practitioner is Sertac. Yes, Professor Sertac. And so now I will give the floor to you, and please start. Thank you.
Thank you. Okay, thank you for your presentation. My name is Sertac Savas. I am assistant professor at Erdi University, Mechatronics Engineering Department from Turkey. And the name of our study is controller gain tuning of a non-holonomic mobile robot via neural network predictor. First of all, I want to talk about the importance to design systems for blind people to increase their integration into their social lives. So in that study, we aimed to design a robotic system and also a control approach which will enable blind people to move from one place to another. And it is decided to design a mobile robot can go to a target point with the least error on a certain trajectory and in a working environment known with its obstacles. So in this direction, we designed a analytical kinematic controller, and it is proposed to determine the control gain parameters using artificial neural network. And we made some real-time experiments to examine the tracking performances of the artificial neural networks. And we made these experiments for two different platform conditions, with and without obstacles, and for two different target points, A and B. In section 2, I want to talk about experimental mobile robot and mobile robot platform. We used a mobile robot designed by National Instruments called Robotics Starter Kit. We selected this second version of this robot, and also it is called DANI, the abbreviation of Data Acquisition National Instruments. It is designed a mobile robot for real-time applications. It's an out-of-box mobile robot, and it has a control card called Single Board Trio 9632, and it is also developed by National Instruments. And this control card has two processors. The first one is 400 megahertz processor, and the second one is FPGA processor, Xilinx Spartan FPGA processor. This processor is really suitable for real-time applications with a high hardware communication speeds, especially in hardware communication speeds, and also a motor driver, a dual motor driver, a power regulator, an interconnection card, two incremental optical encoders, and of course a battery we have on the robot. And in figure 1 we can see the structure and the basic elements of the mobile robot. Also, we made some additions to the mobile robot, an access point, and to obtain the wireless communication between computer and mobile robot, and a plate with two markers. We used this plate for image processing to make the localization of the mobile robot, posture of the mobile robot, and heading angle, orientation to determine the heading angle of the mobile robot, with a camera mounted on the ceiling of the lab, which our working environment place built, and a LED light source. It is important to obtain a stable intensity for the light on the plate for image processing. Also, a portable power bank to supply power to the access point and LED light source. And in figure 2, we can see the final version of our mobile robot and the hardware additions. And we built a mobile robot platform in our lab, Yildirim Mobile Robotic Systems Lab. A camera is mounted in the ceiling of the lab, as I said before, for the localization of the mobile robot to determine the posture of the mobile robot, and orientation, the heading angle of the mobile robot for image processing. And this is called simulated GPS. It's like a bird's eye. It has a field of view of bird's eye. And we used an ultra-wide angle lens, 120 degrees angle with this angle for image processing. And we can see that it needs a hardly distortion correction because of this ultra-wide angle lens. In section 3, I want to talk about the controller design. As I said, we made an analytical kinematic controller. We designed a kinematic controller. And you can see in the following equation the control velocities of the mobile robot. This is called upper level control. You know, in real time, we have two parts for the control approach. And this is the upper level control. Also, we made for real-time experiments some lower level control, just like DC motor velocity control. And in the equation, we can see K1, 2, and 3 as the control gain parameters. And our we proposed to tune these control gain parameters using neural networks. And in figure 6, we can see a usual closed loop control block diagram. And our system, you know, it's a mobile robot, and the output of the mobile robot is posture. So at the beginning of the control loop, we are trying to eliminate the posture error, the difference between reference posture and actual posture. And we multiply this difference matrix with a transformation matrix. You know, we are working on a horizontal plane, so this transformation matrix is a Z rotation matrix. So the controller uses this posture error on the local coordinate system of the mobile robot and tries to eliminate while producing the control velocities, angular and linear velocities, and mobile robots produces the new actual posture. And then we made neural network predictor design. As I said before, we proposed to predict the control gains using artificial neural networks. And we made 90 real-time experiments. These experiments done for, we will see in the following slides. We made these experiments for the target point A and for the platform without obstacles. And we obtained 90 real-time data for posture error E1, 2, 3, and for different control gain values for K1, 2, 3, K1, K2, and K3. And this input-output relationship is taught to two different artificial neural networks. And these were multi-layer perceptron, MLP, and radial-based neural network. These are usually, they are commonly used for the fitting applications, for predicting applications. And finally, we obtained the black box network models for these experimental data. Also, we determined the parameters of the neural networks during a lot of training processes. We made these, the training processes are carried out for different hidden layers neural number and for three different training algorithms and for 3 different activation functions. Also for RBNN, radial-based neural network, the training processes are carried out approximately for 100 different speed values. So in table 1, we can see the parameters which gives the lowest training errors. So we are going to use the networks with these parameters to determine the gain values of the controller. And in the second part, we determined the control gain values, as I said. And now we applied 9,600 different gain values as a simulation way to the network inputs. And we examined the outputs of these networks as the control gain parameters. So we had the chance to do a lot of trials with the control gain parameters to examine what the posture errors they will produce. It's not possible to do 9,600 experimental studies, but we were able to do these simulation studies with the black box of neural networks models. So in table 2, we can find the control parameters, which gives the lowest posture error, mean squared error, values. So we will use these network models and these control gain parameters in the experimental studies to compare the tracking performance of these gain parameters produced with these neural networks. So final experimental studies we carried out. These studies carried out for 2 different platform situations we will see in the figures following, with and without obstacles, and 2 different target points, A and B. And we developed 2 programs. The first one is localization and trajectory planning program. This program developed in a previous study of our teammate. And the main focus of that study is about the program trajectory tracking control program. The control cycle is nearly 35 milliseconds. And as you know, it is really suitable for the real-time applications. And we carried out these experimental studies for the reference linear velocity 0.1 meters per second. While doing the control process of a mobile robot, you have to define one stable reference linear velocity. And we obtained the data for neural network training for the reference linear velocity 0.1. So we will focus for the results, especially for this linear velocity. But also we repeated the experiments for a lower and higher one, 0.07 and 0.13 meters per second, to just examine the tracking performance of the control gain parameters. If these parameters is suitable for tracking the trajectories, or do we need to determine again the control gain parameters for these linear velocities? And figure 7, we can see the trajectories tracked with the control gain parameters produced with MLP on the left hand and on the right hand, predicted with RBNN, radial-based neural network. And in all figures, or in all graphics, we can see the reference trajectory, map boundaries, first of all, as the blue line, and reference trajectory, and trajectories tracked with different reference linear velocities. They are all in the same figure. And this is the map without obstacles for the target point A. If we focus on these graphs, we can easily see that when it is not a challenge path, for example, a linear path, it is easy to track the path for each controller. But if we have sharp turns, the challenge starts, and the heading angle, the orientation of the mobile robot starts to oscillate. So we can easily see the amplitude of the oscillation A and B. The RBNN control trajectory, I mean the gain parameters produced with RBNN, the amplitude of the oscillation is significantly lower. We can see from the figures. Also in figure 8, we can see easy path, a linear path. So we can just say the performances, tracking performances of all gain parameters is similar, close and high. They track the path really successfully. But again, in figure 9, we can see the platform with obstacles for the target point A. And again, for a linear path, it is easy to track, but in turning points, again, oscillation starts. And as we can see, RBNN controlled mobile robot heading oscillation is lower. And finally, in figure 10, we can see the platform, the map with obstacles for the target point B. And again, we can see the faster response of RBNN controlled mobile robots. So finally, for the conclusion, we designed kinematic controller and proposed to predict the control gain parameters with this for this controller. And we made some experiments to investigate, examine our proposal. So we observed that the RBNN neural network predicts the control gains better than MLP, and these control gain parameters have better tracking performances, especially faster response to sharp turns. And also we carried out experimental studies for a lower and a higher reference linear velocity. And for a lower one, we saw that performances are close and high, no problem. But for a higher reference linear velocity, the mobile robot orientation started to oscillate. But still, the amplitude of the oscillation was lower in the RBNN. But we can say that it should be redetermined at rising reference velocity. The control gain parameters must be redetermined. And in future studies, we can suggest by performing a flexible localization approach, experiments can be carried out in a larger workspace or for outdoor applications. Also, the controller design can be improved. Integral and derivative control effects can be added to our controllers. And also different control structures can be tested for this concept of research. And also we thanks to our scientific research projects units of our university for their support to this project, the study of this project. And thank you for listening. That's all.
Okay, thank you for Mr. Sertac. Now it's a question time. Is there any questions? Please open your microphone, and also you can put your question in chat. Okay, so maybe I have a question first. So Mr. Sertac, I would like to ask, because now you set the camera on the ceiling of the lab. Mm-hmm. So I would like to ask if the robot enter to the blind zone of the camera mm-hmm. under some certain case. Is there some strategy to do that mm-hmm, from the robot? Yeah.
In fact, we wanted to use the advantage of studying in a lab. So for an indoor application, just like a platform in the lab, we wanted to use the advantage to make the localization of the mobile robot with a, as I said, a bird's eye field of view. But of course, there are ways to make localization. This is a surge area for the mobile robot to make localization for achieving the localization problem. The first idea for this, it's a LiDAR sensor for indoor applications. But if you go for outdoor applications, you have to use GPS or assistant GPS for these applications. As we know, these devices and these technologies is getting better day and day. And it's of course possible to use these flexible localization methods to take the mobile robots in other environments, working environments, and for other applications.
Okay, thanks.
Mm-hmm.
Is there any other questions? Okay, so if not, I would like to thank you very much for the nice presentation from Professor Sertac, and I will change to another topic. So, Mrs. Maria Gianna, are you here?
Yes, good morning.
Yeah, good morning. So I would like to give the floor to you. And the topic of this presentation is real-time path recognition and automatic control of educational smart car. So please start your presentation and good luck.
Please let me introduce myself. I'm a third-year PhD student at the University of Craiova, Romania, and this paper was done in collaboration with my colleague, Theodor, also a PhD student in the same department. The main topics of the presentation are autonomous driving research motivation in industrial and academic sectors, real-time image acquisition, processing and control for a scale model car, experimental results, and conclusions. It is well known that autonomous driving is shaping the future of automotive development. The main challenges are associated to the real-time perception of the environment and to the real-time processing of this data for vehicle control in dynamic environments. A real-time prototype of the road can be obtained using data from scanners, camera systems, and LiDAR sensors mounted on a vehicle. The vehicle control should consider avoidance of any immediate collision and determination of the path to destination. Industrial research in the autonomous driving field was also extended to the international academic sector. In the last years, the largest suppliers of automotive embedded systems launched through their educational programs different contests that involve the development of autonomous small vehicles. One of these contests is NXP Cup, Intelligent Car Racing. Competitions are held across Europe and North Africa, where student teams race their cars for the fastest time, running on a track of curves, intersections, hills, and straights. As we see, a track model, the pattern is white and the edges are black. The development of the car includes the hardware platform manufacturing and the microcontroller programming. The paper presents the real-time path recognition of the track and the control of the smart car built for this contest. In order to perform the real-time path recognition, real-time image acquisition is needed, and this is done using a camera sensor. This camera sensor module provides a TAOS 128 pixel linear array sensor and a lens. The linear sensor consists of a 128 array of photodiodes, associated charge amplifier circuit, and the pixel data hold function that provides simultaneous integration for all pixels. The output from each pixel is an analog voltage proportional to the light intensity and to the integration time. Images can be acquired in continuous or one-shot mode. The acquisition algorithm was implemented on the microcontroller and is described on the left side, was done based on the timing waveforms from the camera sensor. The clock controls the charge transfer and pixel output, and the serial input defines the start of the data out sequence. The values from the pixels are read in this way. So firstly, the serial input is set to high, clock is set to high, serial input is set to low, and the analog voltage for the first pixel is read. After, all the analog voltage for all the other pixels is read based on the clock cycle. Of course, because we have an analog voltage, an analog to digital converter is used. At the end, the algorithm returns a buffer which contains the values from all 128 pixels. In order to better analyze the information acquired from the camera using the above algorithm, a Bluetooth communication between the car and the computer was established. During a run on the track, the vehicle transmits acquired images from the camera, and they can be visualized using a MATLAB interface. For example, we have here images from a straight path, from an intersection path, from a left curve, and from a right curve. The images show the differences between the white and the black zones of the track. It can be observed that the black edges are at least 3 times less in amplitude than the white zones. The pixel amplitude depends also on the light intensity. The output of the acquisition algorithm is provided to the processing algorithm in order to obtain the path recognition of the track. And the control of the smart car is based on the steering control and on the motor speed control, as it can be seen in this closed loop structure. From the processing algorithm results the path direction of the track. This is converted in a deviation relative to the center of the track with values between -63 to 64, where 0 is the center. This deviation is used for the steering control using a proportional gain. The command is saturated in a certain range based on the actuator works limit, and this is applied to the servo via a motor bridge. The motor speed control is done based on the information provided by the Hall effect sensors mounted on the wheels. The speed reference is defined in the initialization phase of the algorithm, of the control algorithm, and represents the desired speed of the car. this is influenced also by the deviation of the path direction. So if a curve is detected, for example, the desired speed reference will be modified because braking is needed. So this speed reference is then compared to the measured speed, and the PID adaptive control law is used. The command is also saturated in a certain range and is applied to the DC motors via a motor bridge. To keep the car on the track, the data acquisition, elaboration of decisions, and actuation of the car are performed in real time at every 2 milliseconds. As an example, in case the deviation has a negative value, it means that a left curve is detected, and the vehicle should firstly brake and then steer to the left side. The speed set point is firstly decreased for braking by using a variable proportional gain. Then the set point value for the left motor is reduced, while the set point value for the right motor is increased in order to obtain a speed differential control. For a right curve, the speed differential control is applied in the opposite way. Experimental results: the design car participated in the NXP Cup Intelligent Car Racing Finals in 2018. The parameters of the control laws were tuned during racing on multiple test tracks. The final track was assembled just before the contest. And from the official results, it can be seen that the car won the first place with a noticeable difference of 4 seconds than second place. The active learning approach described in this paper has been applied within similar academic competitions. The targeted groups were third and fourth year students from the bachelor's degree program attending the embedded system courses. The grading comparison based on the exam results indicates that the students which took part in this learning approach motivated better their answers, completed their tasks with better results, and they were capable to explain in much more detail the implemented hardware and software solutions. In conclusion, this paper presents a successfully applied learning approach on embedded systems, considering a scale model vehicle used in an international educational program. Considering the main problems of the self-driving perspective, the presented solution for path recognition and control can be used for better understanding the risks and uncertainties which the automated vehicles industry faces in different driving scenarios. The presented learning outcomes show that this approach helps students to improve their technical abilities, their communication and teamwork skills, inspiring them for engineering careers and future innovation. The paper emphasizes the actual concerns in the industry of automotive embedded systems. High levels of automation are desired for vehicles to manage any driving scenario with no human intervention. Thank you for your attention, and if there are any questions.
Okay, thank you, Maria Gianna. And is there any questions for her? Please open your microphone or put your questions in chat. Okay, maybe I have a question first. Maria Gianna, I would like to ask, because this is a very meaningful competition. So what do you thinking about the bachelor's? You said the bachelor student have a course for an embed system.
Yes.
Yes.
For
So
embedded
it's
systems.
Yeah. So it's special for this competition, or it's a general course?
No, it's a general course, but normally from our university, for example, the student teams for these competitions are from third and fourth year bachelor's degree when the embedded systems, when they learn the embedded systems.
Okay, so from this course, you will select some student to join this competition, or just?
Yes, I can select some of them, and of course, the students that want to participate, they want to accept this challenge.
Yeah. So, what do you thinking about from this competition? What kind of the skill the student can improve themselves from the course or from the competition?
From the competition.
Competition, yeah.
Especially the embedded system knowledge, programming knowledge, firstly, and also hardware knowledge, because as I said, the design of the car includes also the hardware platform manufacturing.
Yes. Okay. So, do you have some a plan to set some course just for this competition? Because as far as I know, there are some university has some course just for some competition. Like in Wageningen University, they every year they will intend fire the robot competition from Germany. So they open one course for this competition. Is there any idea or plan to open some course like this?
No, I didn't think to plan such a course only for a competition. Usually when students want to accept this challenge to participate, the groups are somehow coordinated by professors, and yes, they can be considered as a class and they exchange knowledge.
Yeah. Okay. Thanks a lot.
Thank you.
Okay. Is there any more questions? Okay, if it's not any more questions, I would like to thank you, Maria Gianna. Thank you very much for your nice presentation. And yeah, so Darius, do you want to say something, or I just close this session?
I think that yes, as the chairman, you can close.
Oh, your voice is quite low. Yeah.
I think that as a chairman, you can close the session.
Sorry, it's still quite low for your side.
Strange. Just a minute. And now maybe better.
No.
So just you can close and that's it. Okay.
Yeah, yes, I can hear. Yeah, okay. So I would like to thanks a lot for all the presenter and all the participants in this session. And I will close this session and have a nice day. Bye.
Thank you. Have a nice day. Goodbye.
Yeah. Bye.
Bye bye.
Bye.